ce contextual, Lionel.
Thanks. So I'm going to move from yesterday's topic of sand piles to today's topic of activated random walks. And I will just hint at what these two models have in common. First, let me define the activated random walk model. So its definition will look very different from the sand pile, but think of it as an interacting particle system. So again, we'll work on a finite or infinite connected graph, always locally finite graph, and we'll have two species of particles, active and sleeping. If there's an active particle at vertex x, I'll denote that AX, and a sleeping particle be SX. And we'll think of this as a continuous time dynamical system with the following rates. So active particles will jump to neighbors at rate 1. Active particles will fall asleep at rate lambda. Lambda will be a parameter. And active particles can wake up sleeping particles if they're at the same site. So if you have an active and a sleeping particle at the same site, you end up with two active particles there. And this happens instantly. So I'm mainly defining it this way to save on time, but I really don't want to think of this as having this specific time parameterization with continuous time and jump rates. There's a kind of rateless description of this process, which makes it analogous to the sand pile. And without writing down exactly how that works, you could think of them both as kind of interacting systems of interacting Markov chains, where each vertex of your graph has a local chain at that vertex. And these chains talk to each other via the edges of your graph. So I've just drawn what the local chains are in the sandpile case and the activated random walk case. So in the sandpile case, the local chain at vertex V has dV states, where dV is the degree. And the local chain kind of remembers every time your vertex receives a particle, it keeps track modulo the degree of the total number of particles it's received. And remember that in the sandpile, you send out your particles in bursts. Every time you receive, if you have at least dV particles, then you can send one to each neighbor. And so this local chain, it's a deterministic chain in the sandpile case. It just transitions with probability 1. It increments these counts mod dV. But every time it's received enough particles to emit a batch of dV, it goes ahead and does that. So these yellow arrows are emitting particles to the neighbors. And here's the corresponding chain for activated random walk, where there are only two states. 0 represents empty, and S represents that there's a sleeping particle. And the transitions are, so no matter what state you're in, independently of the past, you transition to state S with probability P, where P is related to the sleep rate by its lambda over 1 plus lambda. But how many particles you emit depends on which of the 4 transitions you just did. So there's a whole family of models called the abelian networks, which you can get by varying these local chains. And the advantage of this picture is that it doesn't tie us to a particular time parameterization. So the abelian networks are kind of designed. I should just write down. So it's an example of an abelian network. These were proposed by Deepak Dar. And with Ben Bonds, we proved all the basic things about them. The paper of Dar where he mentions this idea really had a big influence on me. So I think his motivation was renormalization. So he wanted to take a sandpile and renormalize the lattice it was on so that instead of taking the individual vertices as fundamental, you would take some larger block as fundamental. And so he wanted to think, well, if you had a sandpile, but you've zoomed out far enough that you can't see individually how many chips are at each vertex. So you want to sort of abstract what's going on inside a block of vertices. Well, the block of vertices will have some internal state which records exactly how many chips are at each vertex, and it can receive chips from the outside, and it can emit chips to the outside. And so with this picture, you have sort of each block is a Markov chain with communication from, to and from the outside. So I think that was his motivation. He had this paragraph where he says, you can think of the vertices of your graph as automata, and you could think of the particles in your system as messages being passed between the automata. And this really suggested to me like a kind of fruitful way of looking at these systems. We tend to take the dynamical view of like, here's a particle system, here are the rules governing the interactions, now what does the system do? But there's also kind of a computational side to things, where you think of, somehow it's not the particles that are the main actors, it's the vertices of your graph, which you normally think of as just static background. But in this picture, the vertices are the actors. They're automata passing messages between each other. And it suggests more computational questions, like rather than, what does this dynamical system do? It suggests questions of the form, like what can you compute with a network of automata following these rules? Okay, so my purpose today is to write down a bunch of conjectures about activated random walk. And originally these were conjectures for the sandpile, but over the years, people started to realize they're not actually true for the sandpile, and they looked for models where they actually are true, and activated random walk seems like the best candidate. So, no conjectures. So let's start with the simplest initial condition, which is a point source So we're going to start with n particles at the origin, and then we'll stabilize them. So this capital S means stabilize. So we've got these n active particles, and we're going to let them follow these rules until they all fall asleep. So they'll fall asleep at n random sites in ZD. And we want to know where do they end up. And sleeping particles. So this is and the conjecture is that they will spread out to fill up approximately a Euclidean ball, and you'll have a constant density on the ball. Okay. So if you rescale this, then it should converge in weak star to a constant, which I'll call zeta A times the indicator of a ball. This is a ball and RD of volume 1 over zeta A. So conjecture is that there exists this constant zeta A. It depends on the dimension and also on the sleep rate. So if you, it's useful to think of decreasing the sleep rate. So if the sleep rate is very high, then your particles fall asleep almost immediately. And in that limit, that the sleep rate goes to infinity, this process is called internal DLA. I should mention that. So in lambda goes to infinity limit, activated random walk becomes internal DLA. So what is internal DLA? This is the following process. Start with n particles at the origin in ZD. Each particle does a simple random walk until it reaches an unoccupied site and then falls asleep there and stays there forever. So this conjecture is true in the lambda to infinity limit. We know that internal DLA has asymptotic shape of a Euclidean ball, but as soon as you reduce the sleep rate to something finite, we don't know how to prove this.
So this is the Euclidean ball, right?
Yeah, Euclidean ball. And I'll just remark that this is quite false for the sand pile. So if you started with n particles at the origin and stabilized them with sand pile topplings instead of with these activated random walk rules, then instead of getting just a uniform density over a ball, you get a lot of fractal structure inside where your particles ended up, and the limiting shape is believed to not be a ball. So, so this is the first manifestation of universality, that you get something rotationally symmetric here.
And there's no conjecture for zeta A?
For what is zeta A?
Yes.
Yeah, so I'm getting to that. So, yeah, there's no conjectured formula for zeta A as a function of lambda, but there are conjectures about zeta A being equal to some other things with no formula, which I'm about to define. So, more questions? Yeah.
Sorry, I maybe missed this answer. So there is no normalization like
Yeah, I'm hiding the normalization in this. So you rescale space so that this thing fits inside. Right. So you have n particles. So you're rescaling space by order square root or n to the 1 over d dimension.
And is it like already known?
But that's the right scaling. Yeah. Okay.
So, in other words, it's known that you can fit this thing in a bigger ball, and
Yeah.
What do you mean by it's known, this rescaling?
Okay. I think it's known that like with high probability, there's some large ball such that with high probability none of the particles will escape the large ball. So there's a ton of papers by Amin and Leorola and many Lorenzo and many co-authors where they prove that a certain critical density is strictly between 0 and 1, and I think with variants of those arguments you could show that this is confined to a big ball. Okay. So what is that critical density? So that's the kind of second. So this was finitely many particles in VD, but you could start instead with infinitely many particles. So you could start with some stationary ergodic initial condition on ZD. So this is a bunch of particles that all start active. And so here there's a theorem of Rolla, Sidorovicius, and Zindi about what happens if you try to stabilize such an eta with activated random walk. So there exists a critical zeta depending on the dimension and the steep rate, such that let's call zeta the mean number of particles per site. So if zeta is less than zeta c, then eta stabilizes almost surely. So stabilizing means that the odometer function, the function that counts the number of visits to each site, is finite everywhere. number of visits to X. And if you're on the other side, if you're too dense, then zeta explodes almost surely. Your odometer function, meaning that your odometer function is infinite everywhere. Every site visited infinitely often. And so what's cool about this is it doesn't depend on details of the distribution eta. It only depends on its mean. So that's a sort of universality, that a lot of details don't matter here. And even this assumption can be weakened. So Hyojong has a recent result that this is still true if eta takes values in N union S. So S means that some of the particles could be asleep. Okay, provided what? So our result uses its IID, not just stationary ergodic, and of course you need to have somebody awake. So, you know, probability that eta is S is strictly less than 1. Okay, so that's really nice. There's a conjecture. So one of my conjectures with Vittoria is sometimes called the density conjecture. Is that this zeta C is equal to the zeta A from up there. So the density you see from these aggregation experiments is the same as the critical density you see in these infinite experiments. And this was recently proved in dimension 1. I guess actually this theorem relies on this one, so this is also C equals 1. So this is proved in dimension 1 by Hoffman, Johnson, and Yuna. And it's open in higher dimensions. Yeah.
Do you have a conjecture what happens at C to C?
Yeah, I think it probably explodes at zeta C, but
Why?
I don't know. Let me think about that offline. Yeah. Okay, there's a third setup. Which we call the wired activated random walk Markov chain. And this setup, in a sense, oh, maybe I shouldn't write here because these folks can't see. So this is the setup that most closely mirrors the initial motivation of sprinkling sand on a pile. So the idea is that you've got some finite system with a boundary, and particles can escape across the boundary. So you should think of like a pile of sand on a tabletop, and you sprinkle sand on it, and eventually the sand reaches the edge of the table and starts to fall off. So let's do this chain on a finite subset of ZD. So it's a discrete time Markov chain, WT, where the update rule is you add a single active particle at a fixed vertex, let's say x0, fixed vertex, and then you stabilize, but with killing at the boundary of V. So stabilize with killing. So particles that exit V disappear from the system. So in activated random walk, when you might start with a configuration where there's some active particles, but when you've stabilized, everything is asleep. Okay? So the state space of this Markov chain is sleeping configurations. So every vertex in this finite set V either has no particle or a sleeping particle. So then you take that sleeping configuration, you add a single active particle at x0, and that active particle will walk around, and maybe it just falls asleep and you're done. But maybe it wakes up some of these sleepers and they walk around and cause a big avalanche. Okay, so that's the Markov chain. And one thing that's nice about this Markov chain is, so it has an exponentially large state space. So in principle, it might be hard to sample exactly from its stationary distribution. But it turns out for this particular chain, there's an efficient way to sample exactly from the stationary distribution. Distribution of WT. So all you have to do is take the configuration of all active particles, I'll call that 1V, so one active particle at each vertex, and stabilize that. So I claim that this is exactly stationary for the Markov chain. And I just include this proof because it's a good illustration of how we use the abelian property everywhere in this area. So how would you check that this thing is stationary? So consider what happens if you take the all ones configuration and add a single additional particle at x0. Well, one thing you could do is, if you keep the ones around, then this extra particle can never fall asleep, because you're only allowed to fall asleep if the site is empty. So you could just let this extra particle do a simple random walk until it exits V, and then it's gone. And then you could stabilize the rest. So that's one way to stabilize this configuration. Or you could stabilize the 1V first and keep this particle for last. So if you do it that way, you'll get S of 1V. You still have your extra particle around. And now you could stabilize this S of S1b. And abelian property, which is proved exactly the same way as we proved it for the sand pile yesterday, means that any two procedures you have for stabilizing, the law of what you get at the ends will be the same. So these are equal in distribution by abelian property. Right, so this exactly says that whatever I get by stabilizing 1v, if I then add an additional particle to it and stabilize, it doesn't change the distribution. Okay, so we're interested in what this stationary distribution looks like. So let's take an exhaustion of ZD. So increasing sequence of finite sets whose union is all of ZD. Okay, assume it's nice, so good examples to think about are balls or cubes. Okay, so for any Vn, we can look at the stationary distribution of the wired chain on Vn, and we want to pass to a limit. So the first conjecture is if you just count how many particles are in the stationary distribution, so S Vn 1 Vn. So this absolute value on the top just means the total number of sleeping particles, and the absolute value on the bottom means cardinality of the set. So the conjecture is, there exists a density, a number zeta s, depending on d and lambda, such that these converge in probability to zeta s. And the further elaboration of the density conjecture is that zeta s is equal to the other two densities we've already defined. You could look at limits of more than just the density, though. You could look at the actual configurations themselves. And we think those have a limit, too. So let's say pi v be the law of this stationary state SV1v. So the way to think about, we're going to take an infinite volume limit, as they call it in physics, which is like looking at a small piece of a very large configuration. So we'll fix a finite window W to look at, and then look at a growing sequence of sets Vn. So each Vn, we have a stationary distribution on Vn, and we'll restrict it to this fixed finite window. So the conjecture is these measures have a limit. And so by Kolmogorov extension theorem, if you knew this for every w, then you would get a measure, probability measure, say pi zd on infinite zd. So 0s zd. There's another way you could try to get a measure on infinite configurations, which is by going back to our first experiment of n particles at the origin, stabilizing them, and you get some sleeping particles. And you could pick a little window here to look at. So you could take a fixed window here and take n to infinity. So limit also exists for stabilization of n delta 0 restricted to w as n goes to infinity. And we weren't quite brave enough to conjecture that these limits are equal, but maybe they are. We did some experiments that don't conclusively give proof. I mean, they're not obviously different, but it's hard to tell if they're equal. Both of these measures have a weird property called hyperuniformity. Which is a kind of repulsion between the sleeping particles. So conjecture hyperuniformity. In either of the two limits, if you take the so take a configuration with this on ZD with this limiting distribution, and look at the number of particles in a fixed window. So let's say the sum a to x, x a to w. So if you take the variance of this particle count, it's unusually small. So it seems to be growing like a power of w, strictly less than 1. Right, so if these things were independent or even approximately independent, then you would think the variance of the sum of w things would be order w. To make it like a lot smaller than w, what you need is some like kind of delicately tuned repulsion between the particles. So like in one dimension, you take W to be an interval, you're looking at, well, where are your sleeping particles located in the interval? They can't be anything close to IID for this variance to be so small. They have to be like kind of very evenly spaced. Right, so if you want to have a predictable number of particles in any interval, then the only way to do that is to have them unusually evenly spaced. And so there's some kind of strong repulsion between the sleepers in both of these setups, where you do aggregation and when you do the stationary measure. I don't know, that's a puzzle that I hope one of you will solve. Thanks.
Last thing is a conjecture about the behavior of the limiting measure which is conjecture to exist.
Yes.
So, and it is all numeric based?
Yeah, it's numerics based. So if you want to make this like less of a conjecture on top of a conjecture, there's the experiments we actually did were take the stationary distribution for activated random walk in a big box, and then look at the box of half the side length and do the particle counts there. So that appears to have sublinear variance.
Is this for G equals 2 or any?
It seems to be in any dimension, yeah. I mean, of course, we didn't simulate high dimensions, but yeah.
I was wondering between 1 and 2.
Yeah, it seems to be true in both 1 and 2.
And the sort of behavior is also expected for the stochastic sandpile or like for the...
Ah, okay, right. I'm glad you mentioned stochastic sandpile because Nicola asked me to mention that, so since he'll be talking about it tomorrow. Yeah, so after people realized that the abelian sandpile is non-universal in various ways, they first proposed, let's make the toppling stochastic. So instead of whenever you topple, you send exactly one chip to each of your neighbors. You say, whenever you topple, you send, a deterministic number of chips, but each one goes independently to a random neighbor. And most of these conjectures, I believe, should also hold for stochastic sandpile. But it was so hard to prove anything about stochastic sandpiles that Hoffman and Sidorovicius invented activated random walk. And it's still hard to prove things about activated random walk, but we're making more progress on activated random walk. So it's mostly a case that activated random walk is easier, but I think the conjectures should also hold for stochastic sandpile.
Maybe a comment that also Nicolas Florian has a result in dimension 1 for activated random walk at critical density, where he shows that he can speak about this result. There is a sublinear number of particles escaping a segment. So, and this means.
And does the result of Mann and co-authors they imply some other conjectures? Like, do they also obtain uniformity?
Right. So last I talked with Chris Hoffman, he said he's working on some of the other conjectures, and actually I think it was Matt Junger who told me, another of their co-authors, told me they can prove the hockey stick conjecture, which is one I didn't have time to mention, but it's also about the bulk behavior. So I don't think their method so far can say anything about the microstructure, which it seems like you would need that to get hyperuniformity. Well, maybe not, but anyway.
No other questions?
Okay, so if not, let's thank Lionel again.
Okay.